Let us see about approximation of derivatives, impulse invariance method and frequency transformation and bilinear transformation using frequency transformation. Now, what's the design of digital filters from analog filter? Mapping the desired digital filter specification into those for an equivalent analog filter. Now, and then derive the analog transfer function for the analog prototype and transform the transfer function of the analog prototype into an equivalent digital filter transfer function. And there are three types, that is impulse invariant method, bilinear transformation and approximation of derivatives. Now we can see the analog to digital conversion. The first one is the S-plane and second one is the Z-plane. The analog filters stay stable if the poles on the left side of the S-plane is on the left side of the S-plane, and also the digital filter if the poles inside the unit circle, if the poles lies inside the unit circle, and also the left half of the S-plane should map inside the unit circle in the Z-plane, and the j omega axis in the S-plane should map the unit circle in the Z-plane. That is the direct relationship between the frequency variable. Therefore, first one is the S-plane and next one is the Z-plane. Therefore, the system is said to be stable if if all the poles lies on the left half of the S-plane and also the poles must lie inside the unit circle in the case of digital domain. Now we can see the design one by one. Design of IAR filter using impulse invariant method. First, from the given specification, find HA of S, then select the sampling rate of the digital filters, and it is called as T seconds per samples. Then we are expressing the analog transfer function as the sum of single pole filters, that is HA of S is equal to summation k equal to 1 to n Ck divided by S minus Pk. And also the fourth step is we are just computing the Z transform for the digital filters by using the formulas, that is we are just mapping from S-plane to Z-plane. Therefore, omega equal to omega Z. Therefore, in the S-plane it is represented as HA of S, and in the Z-plane it is represented as H of Z. Then we are just, that is for high sampling rate, if T is lesser, then here when we are just taking the T outside of this sampling in the case of impulse invariant method, and also we are just converting the analog domain into digital domain. Now while we are solving problems, let us see one problem. For the analog transfer function H of S equal to, they are given, determine H of S using the impulse invariant method, and they are also given the value for capital T equal to 1. In this, we want to split this by using the partial fraction expansion. Therefore, while we are applying the partial fraction expansion, since we are having two terms, we want to find the value for A and B. And finally, we are just converting, that is the S-plane is converted in terms of Z-plane. Therefore, we are just finding the value of H of S. That is we are expressing H of S in terms of H of S, where we are substituting T equal to 1. And finally, we are simplifying, and finally we are getting the digital transfer function. And also here in another problems, if sampling equal to 5 seconds means we want to find the value for time, that is T equal to, here they are indirectly given the value for T. Therefore, T equal to 1 by F sample. Therefore, T equal to 1 by F. Therefore, since T equal to 1 by F, F equal to 5. Therefore, T equal to 0.2. Therefore, we are substituting and finding the value. We are just converting the analog to digital and finding the value for H of Z. Next one, the second one is bilinear transformation. It is the mapping that transforms the j omega axis into the unit circle in the Z-plane only once. Therefore, we can avoid the aliasing of frequency component that is occurred in the impulse invariant method. And warping effect, that is omega, and that analog omega and digital omega represents the analog and digital filter frequency variable, that is omega equal to 2 pi t tan of omega by 2, and for smaller values of omega equal to 2 pi t omega by 2. That is by substituting the value, we are just converting omega equal to omega into t. That is warping, that is this is for the smaller frequency, this is for the larger frequency. For smaller frequency, omega is directly proportional to capital T. In the case of larger frequency, both variables are showing in nonlinearity. That is, for higher frequency, there is the distortion seen due to the nonlinear relationship between the omega and analog omega and digital omega, and this is said to be the warping effect. Pre-warping, The warping effect can be eliminated by pre-warping the analog filter. This can be done by finding the pre-warping analog frequency using the formulas, that is omega equal to 2 by t tan of omega by 2. While we are finding the passband attenuation and stopband attenuation, we are finding using the same formula. And the design procedures for bilinear transformation is: first step is, from the given specification, find the pre-warping analog frequency omega. And second one, just we are finding the value for H of S for the, that is the analog transfer function. And next we are selecting the sampling rate of the digital filter, that is t per second per sample. Finally, after finding the value for H of S, we are substituting, we are just replacing S by 2 by t 1 minus Z inverse by 1 plus Z inverse in second step. Finally, we are getting the value for H of S. Now let us see one problem. Apply the bilinear transformation to the given transfer function and they are given the value for capital T. Find H of S. Here, since they are given the value directly, then T value is also already given. Therefore, just we can replace S by 2 by T, 1 minus Z inverse divided by 1 plus Z inverse, and finally by simplification we are getting the final result. And here, this is another problem. In this, they are giving the cutoff frequency and also the alpha p and alpha s. Therefore, by substituting the appropriate values in that, we are just finding, that is we are finding the value for capital T, and finally we are replacing, that is s by 1 minus z inverse divided by 1 plus 2 by t into 1 minus z inverse divided by 1 plus z inverse, and finally we are finding the value for H of S. And the last one is approximation of derivative. In the case of approximation of derivative, when we are considering the, when we are seeing the impulse invariant method and bilinear transformation, it is somewhat simplest. That is, we are just replacing s by 1 minus z inverse by divided by capital T to find the value for digital filters. That's all. Thank you.